which one of the following is incorrect with respect to property indicated? Here fluorine, chlorine, bromine, 3 elements are given. The electronegativity value you should know, electron affinity, oxidizing power and bond energy values you should know. Okay, first we will see first option, electronegativity. Electronegativity of fluorine is greater than chlorine, greater than bromine, than iodine. This electronegativity value. Hence fluorine greater than chlorine, greater than bromine. This option is correct one. And second one, electron affinity. Electron affinity, you see chlorine is greater minus 349 than fluorine, than bromine. So this option is also correct. And oxidizing power, you see oxidizing power, fluorine greater than chlorine, greater than bromine, than iodine. This is from electrochemical series. Okay, so this option is also correct. So bond energy, when we come to bond energy, here you see bond energy of chlorine greater than fluorine, than bromine, than iodine. But here what is the option given is fluorine greater than chlorine, greater than bromine. It is wrong. So option D is the incorrect statement with respect to property. Option D for bond energy, chlorine greater than fluorine, than bromine. Here you see bond energy is inversely proportional to bond length, and bond length is directly proportional to size. Okay, size of iodine is greater than the size of the fluorine. Okay, next question, second question. So option D is correct. Which one of the following sets indicate the correct variation of electronegativity? Here you have to know the electronegativity value of fluorine, nitrogen, oxygen and carbon. For carbon it's 2.55, nitrogen it's 3.04, oxygen 3.44, fluorine is 3.98. Hence here you see electronegativity of fluorine is greater than electronegativity of oxygen, then electronegativity of nitrogen, then carbon. Okay, here you see in this option, option A is correct. Fluorine greater than nitrogen, nitrogen less than oxygen, oxygen greater than carbon. Hence option A is correct. Third question, nitric oxide NO has electronic configuration with including K electrons, sigma bonding molecular orbital electrons given, sigma 2s2. This was the given MO configuration. Now you have to calculate the bond order. Here 4 options were given. Ionization to form NO+. So in all the options they are given the ionization to form NO+. So NO on ionization gives NO+. And option 1, its bond order decreases and bond length increases. Its bond order and bond length both decreases. Bond order and bond length both increases. Bond order increases, bond length decreases. 4 options were given. We will see this question. Now you take nitric oxide NO. Here you count the bond order, you calculate the bond order. Bond order is nothing but the number of bonding electron minus number of anti-bonding electron. Here number of bonding electron is 2, 4, 6, 8. 8 minus 3, 2 plus 1, 3. 8 minus 3 divided by 2 is 2.5. So bond order is 2.5. Nitrogen has a double bond and one dotted bond. Okay, so bond order is 2.5. When this ionizes to NO+, now you calculate the bond order. Here number of bonding electron is 8, 2, 4, 6, 8 and number of antibonding, from antibonding orbital, this one electron will be left. So in antibonding orbital you will get only this 2 electron. So 8 minus 2 divided by 2, which is equal to 3. The bond order is 3. That is, NO plus has triple bond. So here you see the bond order increases and bond length decreases, because bond order is inversely proportional to bond length. So it's a concept. So option D is correct. Answer is answer D. The states of hybridization of nitrogen in the species NO2 minus, NO2 plus and NH4 plus. The series of hybridizations was given. You will see this question. Here first you count all the valence electron in this shell and divide it by 8. On dividing by 8 you will get a remainder and a quotient, and you divide the remainder by 2. This is a shortcut trick to calculate the hybridization. Now you get a hybridization corresponding to that number what you got. For example, first you will see, if the number is 2 means it is sp hybridization. If it is 3 means it is sp2 hybridization. That is 1 plus 2, 3. If it is 4, it is sp3 hybridization. If it is 5 means sp3d hybridization. Let us take hybridization of nitrogen in NO2 plus. The total valence shell is 5. For nitrogen it's 5. There are 2 oxygen, so 6 into 2, and for plus charge you have to minus 1, so it is 16. 16 by 8 is 2. Quotient is 2 and the remainder is 0. So it is a sp hybridization. sp hybridization. Next, NH4 plus. In NH4 plus, total valence electron you count it. For nitrogen it is 5. For hydrogen, so totally you will get quotient 4 and a remainder 0. You will get sp3 hybridization in NH4 plus. In NO2 plus, NO2 minus, nitrogen 5, oxygen 6 into 2. Here you have to add 1 electron, NO2 minus, so plus 1, 18. 18 by 8 is 3. Quotient 2, remainder 2. So 2 plus 2 divided by 2, that is 2 plus 1, 3 is sp2 hybridization. Hence answer is B. sp NO2 minus, sp2 sp3 hybridization. NO2 minus is sp, NO2 plus is sp2, NH4 plus is sp3 hybridization. Next question. Superacid, which is known as magic acid in a solution of, here you see magic acid, we call as magic acid, that is called superacid, consisting of a mixture of 1:1 molar ratio of fluorosulfuric acid, HSO3F, fluorosulfuric acid, in antimony pentafluoride. Hence the correct option is B. It is superacid is fluorosulfuric acid plus antimony pentafluoride, Sb5, in 1:1 molar ratio. We call it as superacid. Next question, sixth one. Two hypothetical acid, you take two acids Ha, Hb, have dissociation constant 1 into 10 power minus 3 and 1 into 10 power minus 5. Two concentrations are given respectively in water. How many times Ha is stronger than Hb? Now the strength of an acid is directly proportional to the square root of dissociation constant of acid. So now you calculate the relative strength of the given acid. The acid strength of Ha and divided by Hb is equal to square root of dissociation constant of Ha by Hb. So you will get the ratio 1:10. 1:10, 1 by 10. So it is the answer is A. It is 10 times. So Ha is 10 times stronger than Hb. This was the answer. Next we go to 7th question. The lowest visible spectral band in an octahedral nickel 2 complex is due to the transition. You see, in this nickel 2 complex, first there are 3 bands. This nickel 2 octahedral nickel 2 complex gives 3 bands. One band is from A2G triplet T1G triplet and A2G triplet to T1G triplet, and third band is A2G to T2G triplet. Here the correct option is C. Next question. So they are asking which is the lowest band. Okay. Next question. Which one of the following complex has highest magnetic moment? You have to calculate the magnetic moment. That is, you have to calculate the number of unpaired electron in each complexes. Let us calculate. Higher the number of unpaired electron, higher will be the magnetic moment, mu. First you take the first complex FeCN6 4 minus, the central metal ion has Fe2 plus, which is the cyanide ion is a strong ligon, so it is a low spin complex with a D6 configuration. So all the electrons gets paired and there is no unpaired electron, so mu, magnetic moment, is 0. Now the second option is VOH2O 5 times, and this was a wrong option. This was not a octahedral complex, so we leave it. This was not also ruled out. Option A is also ruled out. Next we come to third one. CrNH36 3 plus. It says chromium 3 plus is a D3 and it has 3 unpaired electron. So 3 into square root of 3 into 3 plus 2, which is 3.87 bm mu. And we come to the fourth option. It is COH2O6, which contains is a D6 metal ion, CO3 plus cobalt 3 plus, which contains 4 unpaired electron. So square root of 4 into 4 plus 2, 4.9 bm. Hence it is the highest magnetic moment. So option 4 is correct. This is also ruled out. So first one contains no unpaired electron, and the second one is ruled out, and third one it has 3 unpaired electron, and the fourth one you see 4 unpaired electrons. So it has the highest magnetic moment. Next question, 9th question. The reaction is an example of. The reaction is an example of. See here. See, this reaction is nothing but a inner sphere electron transfer reaction, where chlorine acts as a bridging ligand. So option A, C and D were ruled out, and option B is correct. It's an example of inner sphere electron transfer reaction. 10th question. Predict the number of metal-metal bond, molybdenum bond in a molecule using 18 electron rule. You have to calculate the 18 electron rule. Now you take this complex. The total valence electron is 30, and 18 into N minus A, this total valence electron, is nothing but B. That is 36 minus 30, which is equal to 6. Okay. Now you divide the 6 by 2, you will get 3. That means it has MO triple bond MO. That is the number of bonds present between the molybdenum and molybdenum is triple bond. Hence answer is C. Answer is 3. Next question. The product of the reaction you see this is viscous complex. When viscous complex reacts with methyl iodide, what will happen? This was the question. Now we will see. This was the viscous complex, iridium complex. Now you add CH3 methyl iodide, you will get like this. This methyl iodide will be added and you will get the product. That is, answer is B. And option C was ruled out. Option A was ruled out because no COCH3 is formed, and option D was ruled out. Option B is correct. You see other viscous complex reactions. I have given here the viscous complex reactions. When viscous complex reacts with the oxygen, it forms a bridge complex. When reacts with the hydrogen, it's a, you will get like this compound SO2. When viscous complex reacts with the SO2, you will get the product like this. SO2 directly adds with this. Similarly chlorine, similarly HX, carbon monoxide, will get the trigonal propenyl complex. HgCl2 will get HgCl, and CH3I we have already seen it. So this is the reactions of viscous complex. And the 12th question, the correct order of CO stretching frequency in the series, that is VCO6 minus, MnCO6 plus, and CrCO6. Yes, here you see why the carbonyl stretching frequency of the given metal complex are reduced. We expect that expected value. Here VCO6, it is 1860 centimeter. CrCO6, it is 2000 centimeter. MnCO6, it is 2090 centimeter. So the observed CO stretching frequency due to this stretching frequency occurs due to pi-pi back bonding of carbonyl group with the above metals. But the stretching frequency of free carbonyl compound CO molecule is 2143. Okay, so option here, the option C is correct. Manganese has higher frequency than chromium than vanadium. So option C is correct. Next question, the complex that would show DD absorption band in electronic spectrum, it is this one is a charge transfer spectra, and this one is also a charge transfer transition. This one is also a charge transfer spectra, and this one shows DD transition, that is potassium ferrocyanide, shows DD band. Based on Wade's rule, predict the structure of metal cluster Fe4C CO12 2-. Now, what is the type of this compound? Whether it is a nido, arachino, closo. Octahedral, no, this D was ruled out. Okay, this was not octahedral. So it may be nido, arachino, or closo. Now the number of skeletal elements is 14n. It's a 56. Valence electron is 62. It's a, now it is a 14n plus 6 format. 14n plus 6 means it is a arachino compound. 14n plus 2 means it is a closo. 14n plus 4 means it is nido. 14n plus 6 means it is arachino. Just you remember this one. And this is the structure. I have given the structure of this compound. Structure of this compound. The metalloenzyme involved in the key step of the skin pigment melanin formation is, answer is C, tyrosinase. It is not superoxide dismutase, it is not myoglobin, it is not nitrogenase. Answer is tyrosinase. We will meet in the next video, that is part 2.